Community formed a community, international community, consisting of various countries, from experts from various countries, and is trying to follow this up very seriously. Clarence has been patented as well. Clarence in this presentation will be repeated again and again because of the big stuff that he's done. Before getting into technical stuff, very briefly about MPLS and engineering, what it was, what it would be, etc. 20 years ago, MES technology was introduced and helped a great deal in various areas. Various service providers, had VTOS, etc., and the various service providers started to work on these. And when MPLS was introduced, we had two main protocols. RSPVT, which is used a lot in engineering, and MPLS. Many services having to do with the MPLS are covered there. LPP has a problem. Of course, for years we've been working with this. We didn't have much problem, but from the point of view of someone who's want to develop this on his big screen, we see that LPP has a strange pattern. LVP used to do latent distribution work. The idea is not to think about something that was, or criticize something that was developed 20 years ago. The question is, what's happening? It's not label distribution in ITP. Everything that's happening, why should I do something that is coversion, version 3, etc. All of this is something that's very important. There's a very important problem here. IGP, LDP, etc. In synchronization, if it's not done properly, there'll be a black holing happening and you drop. So they wanted to have an RSP there, 54646. Regarding LDP, we talked a little bit from the point of view of bandwidth admission optimization. I want to tell you about the bandwidth, optimize it from the point of view of bandwidth protocol. There's a protocol called RSPBT, was generated and we used for years. ISBP in nature has been designed for QS. So it was used for LSPP. RSPT, VPT, what does it do for me? It's virtual circuit such as LTM or old stuff started from a point and go forward hub by hub. I emphasize hub by hub. That is everything that's happening in the LVP protocol and RSVPT. They look at things from hub by hub. It's not possible to see I look at 2 hubs further down or 3 hubs further down. They're looking at it hub by hub. There's a circuit in VLCPT. Hub by hub. It starts from one place and moves on to another place. Why do I want to use RSVPT? Because my network, I want to optimize it from the point of view of that. Do I have the full statistics of the whole network or not? If I'm going to start one point and end at another point, this doesn't cover all what I need. As a result, full mesh MPLS starts. What does it mean? It means from one point to any point, I should have a TE tunnel so that I would have this full statistics of the whole network. For example, if I have two routers, is n to the power 2, that's 100 tunnels. If I have 100 tunnels, 100 or more, well, what happens then? Over the past 10 years, we've had operators who had to, they had about more than 50,000 MPLS tunnels. But why so much complexity? Do we gain anything from this? And MPLS according to RSVPT, was set up and is working. This network is working. First of all, I look at three conditions. First of all, suppose a network has been designed well on the basis of good capacity planning. And when you want to have MPLS strategy engineering, you have traffic engineering, you should have very good capacity planning. Capacity planning doesn't come with experience. You should have a full comprehensive software to have proper full monitoring. Suppose and assume we have a network that has carried out proper capacity planning and it can provide various bandwidth that it needs under various conditions. Does it need NBSP? No. Why should they make their network so complex? Suppose we are under a different condition, MPLS in a network that where the bad things happen rarely, that is the congestion can be borne. That is the congestion that occurs. Doesn't take too much time, doesn't drop the traffic too much, I can bear it. Here, maybe I might need MPLS because if my capacity planning has been good, since I can bear the congestion, I don't need that much. But there are certain conditions, special conditions. The few minutes that I have cut off, I can't bear it. So for those few minutes, I need a technical MPLS tracking engineering. But the traditional RSVPT doesn't do this for me. It doesn't do it instantly. You should always have to tunnel from anywhere to anywhere, and always you should send your IP traffic to your tunnel. Why? So that 5 minutes per year there might be a congestion. That is, I should bear so much complexity with the idea that 5 minutes per year I might have a terrible congestion that I cannot bear. It'll be like this, as if for a special rainy conditions, which according to statistics happens one day a year. Every day you put on your gear-long coat, walk with umbrella, boots, etc. No, it's not logical at all. Now I go back to one of my previous slides on RSVPTA. You see, we're not saying that RSVPTE wants to be transferred, or we rather want to criticize them and say people had done a terrible thing. Not at all. They did a very good thing, because 20 years ago there was no solution that would be able to take care of it from the point of view of bandwidth optimization and optimize the network. It was a solution. It wasn't optimization. It was the only solution. The second option for convergence of network, it was the only technology, the only solution that had fast rerouting. Do you have any other technology that you knew about 20 years ago that could take care of this? No. The question is, LDP and RSVPT solutions, do they satisfy the needs of modern networks today or not? RSVPTE is different. ECMP doesn't understand this. That is when you want to load share your traffic between several things. You can't. You can only go through one route. The most you can do is to have a backup route, backup track. So if we want to have a good MPLS-TE, we should tunnel from anywhere to anywhere. We should tunnel from anywhere to anywhere. If we want to emulate ECMP somehow, I should have several backup groups n squared to the power times k. That's so much tunneling, so much complexity, traffic that is required for only a few minutes for a special condition. In most cases, what we have helps you in traditional MPSTE is your IGP. So it doesn't do anything special or strange. With this introduction, I start talking about segment noting. So what, especially in MPLS in the past we had, was a terrible complexity, but it's not scalable either. Now, we should simplify our network more, give it more capabilities, be able to answer to our needs today. Very simple. Segment routing, what does segment mean? Suppose in the top topology that you can see, we want to go from CE1, the traffic is going to CE2. I want to say that let's go from P3, P6, and PE2. What does segment routing do for me? I have determined 3 points on my route. Segment routing, what does it do for me? Segment routing says you have a number of points on your route. This is the IS OSPF that you want to run. Run it to any point that you want. When I want to have this kind of traffic, I'll have 3 segments. One segment, they are in blue. You want to go from C1 to P3. The first segment is quite clear, it's in blue. When you look at the costs, compare them in segment 1, you see that both routes are equal, so no need to go from up there or down there. You can have ECMB, I can load share. Load share is done up to this point. Then in continuation, I get to the next point. From the next point to the following point, I decide whether can I do ECMP or not. If I can, I can. If otherwise, I have the most optimization efficiency. You've started up an expensive fiber optics route. Why not? You can't not use it. This is the basis of our thinking in segment routing. The client says, I want to go from Brussels to Rome. In my head, I thought I started from Cottado, Switzerland. On the way, I thought, well, can you hear on the radio whether this route is closed or not? If I know, instead of going through Cottado, I go through Geneva. This is the main idea of segment routing in my head. So when I tell you I want to go from this point to so-and-so address, I don't tell you I'm going from here to there, to there, to there. I give you 2, 3 main points. I go there, from there go to the next point, and you can get to your target. When you find the main points, then, those points, you can decide whether I have ECMP to the first point or not, second point or not. This is the basis of segment routing. Now, we have a lot to say today. I hope that you won't be patient. I know this is the second day after lunch. You're tired. But these are valuable stuff that we can talk to each other about. Segment routing in one slide. You'll have some questions. We'll try to answer the questions in the following slides. Segment routing is the eliminates RSVP and you don't need LDP nor RSVP. Everything is done by segment routing, but at what layer does it do it for you? If you remember, when we were talking about MPLS, double tagging, you can have double tagging, different labels you can have. One label can get transport label or whatever. This tab label can take you to the ultimate router. You can have other labels called service label come on top of determine the VRF or tell you which VPLS you are in. Segment routing at this step is determining this transport label. At the service label, you can have your previous labels as well. It has nothing to do with segment routing. similar to MPLS VPN or VPLS or at service layer. There's nothing equivalent to compare it with segment routing. They use EVPN technology. They can be compared to EVPN technology. EVPN has more capabilities compared to what we had in the past. More options it gives you. I was going to talk to determine certain points on my segment routing. How do I determine those? Identify, give them SID, segment ID. Now I should get myself to the segment ID first, go to segment ID 1, then SID 5, and SID 10. Now, as you can see, P3 router has a prefix SID 16099. That's the number. In P2, we have another prefix SID 16007. These are the SIDs. What is a seed, and etc.? What does it mean? Well, I'll talk about this. I have to get to the end of the route, but IGP makes the decision. It says, in order to get to some other place, this is your best route because this is the shortest route, because I have set up the tree, I know which the best route is, so now you're going through these routes, these points, point to point, segment by segment. The best route is determined. While ECM, if we have ECMP, parallel tracks will be used. Parallel routes will be a very important point regarding comparison of MPLS and segment routing. I don't know how much you are familiar with MPLS, how much you've worked with MPLS, but as in the general MPLS discussion, the issue, what we have, topic is when your traffic is moving, your packet is moving, gets to route.
When you're going towards a certain router, we have the in-lay and also the outlay. And then, of course, we have different labels with different prefixes. That is to say that if we have 10 different routers, there is a label for every single prefix which is supposed to be there. Therefore, I learn a label from this aspect and another label from another aspect. We have to actually create many different labels, and a lot of your space would be occupied. But this doesn't happen in segment routing, and of course, it'll stay constant to the different posts. And this is not to do with the meaning that is actually happening in APLS. In this picture, over here in this slide, we are supposed to get to the last point to get to C. It is 16092. It remains the same. It's not taken away. And of course, because it's using the data plane, the inbound and the outbound are also being used because they're still using an old hardware. But the labels and the bands are the same until they get to the point which is needed. When they get to the required point, the label stack actually changes, and we go towards the next seed until we are able to get to the very last point. Another point is actually the highlight that we have down here. If you remember, we had penultimate hop-hopping, and before we get to this part, the header was taken aside, and when we're talking about performance, there's quite a lot of application. When we get to any point, there is a penultimate pointing. We can actually continue this segment thinking. The segment routing is source routing, because whatever happens is at the very first router. Your entire fabric and the whole network does not get involved because the first router actually completes the stack. It's just that the stacks are changing, and it's not supposed to undergo any further changes because it's the source which actually makes the decision, and no source is being kept. If you use this procedure, all the routers are being involved and engaged. What is segment? It's actually the figure which is over here, and each segment is actually an identifier which is given to the service, or it is related to the service. And if we're supposed to use this service, then we'll have to take one CD because you can use seed, you can use service training, and go from one part and then go to the other part, use firewall and use other procedures. Forwarding state, everything is in the first, everything gets determined in the very first router. And then we have the imperial state plane. At the moment, it is noted whether segmenting is the same router. No, it's not. At the moment, when you actually create a technology, you cannot say to the entire world that change your complete hardware because there's being change. You need to do it in such a way that it could work with present day hardware as well. Alongside this, this discussion of SRv6 that my friend will talk more about. It's actually being implemented. They're not using this procedure. They're using the header of IPv6. It's got nothing to do with that header. Segment routing. The model of segment routing, as noted, is actually centralized and distributed. It's been designed in a centralized, distributed modality. Or that, there is actually an SCM controller up there which could decide in a central fashion. Your control plane could be inside the router, or it could be inside an external organism. And it could be IPv6, or it could be the other kinds, or MPLS. Your path option could either be dynamic or explicit. If the MPLS, if you know MPLS traffic engineering, the tunnel that you actually create, you could say that go through IP1, IP2, IP3, and so on and so forth. And of course, there are some segments that we are working with, and all these segments, the numbers are very important. The number of these segments should be unique, and you cannot have the same segment. Where does this come from? We have different models of segment ID. Some of them are global, and they have to be distributed, and some of the other ones are local, and they need to be unique in their own local typology. The different kinds of segments, if we look at them, and IPG and PGP, they have their own segments. And the IGP are divided into two kinds, prefix segments and adjacency segments. What is adjacency? Adjacency is between the two links of the router. It's very local. Now, amidst this, there could be a switch. There could be 10 adjacency segments, for instance, based on the number that they have. So adjacency seed is not unique in all of the network. It should remain the same in the local. But in all your IGP, if you have OSAF, it should actually be unique. And then, of course, we have PGP segment, which has its own prefix, and PGP could actually have segments for itself. And we have a segment ID that we have talked about later on. So we have a prefix seed and the adjacency seed, and some of them are their own IDs. Every link is actually an adjacency seed. Adjacency, of course, the name implies being next to one another. Adjacency means that there should be local, unique in the local stage. Well, we talk about a prefix seed. We have something called segment routing global block. What does this mean? It's actually sRGB, and it is arranged, and inside every single router you need to have an sRGB, and by default it starts from 16,000 and it goes on to 19,992, and you need to have prefix seed, and it should be chosen from this range, and you need to give an index to your router. You might get, for example, the prefix of 1, but the prefix would be sRGB, and at the beginning of the sRGB up to the rest of it, if it starts from 16,000 and goes on to 19,000, and if you want to continue going, it's actually more to be calculated. Now, about node segment or prefix seed, we've already talked about this, and we will talk about adjacency seed. It's a very simple topology. It's actually a consideration of the behavior of the different systems. In the classical MPLS, we've had POP, we've had router, and the ID would actually be included in the MPLS. In the mid routers, until the time we get to the first point, then we will have swap, and then we'll get to the hub. One hub before it's actually there. This is what we were talking about in MPLS, of course. Now, within a special system, it's actually 16,065, and therefore nothing is actually changed hub by hub, and then of course it becomes much more complicated. Generally speaking, we we get more involved with the protocol, and we will talk about this more. The adjacency seed, we said that actually it affects between the two different routers, and it is actually something which is being allocated to sRGB, and we are working from 23,000 to 26,000. Outside this is 24,000 and beyond, and therefore we are allocating different adjacency seeds. The figures that you see are either 24,000 or 24,001. You don't see anything outside this, and of course there are no more links outside. There is actually a point which existed in the outside LPRS, and it doesn't exist anymore outside this system. When you bundle a few channels together, you couldn't actually tell your traffic engineer to go through the second link of the bundle. You couldn't have done that. But when it comes to segment routing, for every linking that exists in the bundle, there could be an allocation of a specific procedure. You have two series of adjacency seeds. One of them is actually allocated to the specific bundle, and you would be able to allocate the traffics. We want to go through an adjacency seed. I could actually tell myself that whether I could go through this node or the other node, and this is the whole concept of adjacency seed. Because when you want to specify and designate the procedure with much more precision, you would use adjacency seed. There is the possibility of using this in combination. That is to say that go through some of the procedure with adjacency and the other one with prefix. This is called combining segment. we are going up to 16,700, and then to 24,078 with adjacency seed. Okay. Another point that existed in the previous procedure, but not in the modern system, you're not supposed to label all the traffic. What you need to do is you need to label the prefix seeds only. That is a prefix which are related. But if you have the prefix seed or the IP of the loopback, if you trace this, you will see what is happening. You actually choose a loopback without a prefix seed, and underneath this, you would say, for example, the seed is, for example, once my sRGB starts from 16,000, therefore the label would be 16,001. Therefore, a seed is linked to a router. Now, with the ones that we actually chose the seeds for, they would turn into labels. But if we trace them, the IP, we're doing actually IP forwarding. In the previous procedure, there would be higher speed. Of course, this was for a long time ago. And of course, the speed of the packet transport would be higher. But when we are talking about high-end routers, and also this will not have much meaning and much concept.
To say that I only use it for speeding up, there's no, it doesn't. It becomes meaningless. So we don't need to keep labeling our stuff. So we talked about two of the SIDs, prefix SID, and for each node, and in the range of our sRGB, and adjacent SID is in that link. Now we have anycast SID. This means a group of nodes with different prefix SIDs and give them a unique and single SID, that is routers 30, 40, 60, and can have anycast SID 200. It can have various applications. In fact, when you send to the 200, it can use any of its links. It can have ECMP, CAP, application, etc. If you want to connect one AS to another AS through BGP, through multi-routers enabled to you, is more than you can use this to distribute your traffic and use different nodes. Now, I am sending traffic to 90, but in fact, in the middle node, I say, go to SID 200. All of this in the middle, the green one, is SID. It's 200. And the cost is the same. So the traffic goes through both of them. I want to go to 200. I go 200. As long as I'm in this green rectangle, the 200 will be there unless I get out of it. It's all 200. In one hub, before the next hub, it's taken off and PHP occurs, and I get to the final node. So we talked about prefix SID, adjacent SID, anycast SID. Now regarding BGP, I talked a little bit. I will talk more about it later. Now we have a binding SID. Suppose that in the blue part, that is, you have a line, you can see from the left to the right, it's blue and then red and green. Suppose these are different domains of your network. That is, your network it comes into three parts. Different IGPs have been run in different administrations even. What you want to do is take the traffic from node 1 to node 10. When you have different IGPs, your topology of your database is limited to your own domain. You don't know anything about the next domain or the following, the domain after that. So you can't see the SID, the SID over there, unless you do redistribution. If you do that, nothing good will happen, because with redistribution, the topology of your database is not transferred there. That is, when you give me a prefix SID through redistribution, I only learn that SID, prefix SID. I will not know about the topology. Now you want to send your packet to different places. I use the binding SID. What does it mean? Binding SID has various applications. They are listed here. I have some, let me give you an example, some conditions. I'm going to go through 10 routers. Out of all these, if I'm going to go through all of these 10 routers, my stack should have 10 labels. Then I will have the MTU problem. If I have 200 hubs over there, I can't put 200 stacks or 300 stacks. Because there must be a solution, because everything happens from hub 1 and label stack is formed on the first hub. So up to the final 200, you have to use all the labels. You have MTU problems. So label stitching is done. It says get to that hub with a binding SID. Then it'll open into 3 others. It goes forward, opens up to 3. Binding SID in node 4 is 30, 4, 10. If I get to 30, 40, 10, what happens? 30, 40, 10. 30, 40, 10 in router 4 has a meaning. It says if you give me 30, 40, 10, this means that I should go 3 hubs forward. I go forward. This is what it means. Go to 16006, 16007, then go 3710. That means the next binding SID. So you're going through several domains this way. So when you are going to have a large label stack, you can compress it this way. If you have multi-domain, multi-area AES, you can send your traffic through. If you have BGP, to mix up your BGP, you can do this. So binding SID has a very important role to play. We shouldn't forget, we have learned prefix SID, adjacency SID, anycast SID, and binding SID. Now we're going to talk about BGP. We said BGP uses its own SID. All the connections that you can see are BGP connections. BGP2 uses an sRGP. The sRGP of BGP has nothing to do with the IGP. This is 16,002, 23,099. Has nothing to do with that. This is for prefixes, BGPs. The other one is for RGP prefixes. For your BGP, you determine a SID. You say you want go to this BGP neighbor, to that BGP neighbor, through segment seeding. Through route map or route policy, you give an index to the router. It adds that index to the sRGP that you had said, and a BGP prefix SID is given to it, is allocated to it. What's interesting that we talk about today is you want to say how to get out of which BGP neighborhood I should get out. I have 2, one Hucom, one Turkcell, say. The first hop, for example, TRC network, have it in mind, infrastructure. Different operators, Shuttle, Pass Online, Hamra Haval, they are connected to all of these providers. A node is connected to Shuttle. Another down there is connected to the gateway. This gateway is connected to Turkcell and also to UCOM. You want to go from the initial node, which is connected to Shuttle, you say that when I get to the end, my traffic should go through Turkcell or UCOM. So you should give SID to your UGP neighbors. It's called Egress peering engineering. This is what it's called. The neighbor doesn't know about this. Everything is local in your network. I have 2 friends. Number 1, I said 2, another number 2. This is what I have in my mind, in my head. Now I'm in router 1 for router 2, which is my BGP neighbor, and I'm using eBGP for it. It's outside my domain. I allocate a SID to it, 312. When my traffic gets to router 1, it means that I can determine a route, hop by hop, it goes to 1, and from there ultimately It depended whether to go to BGP neighbor 1 or 2 or 7, I beg your pardon, 2 or 7. This happens through EPE, Egress peering engineering. In fact, the gray label is your EPA label. This is your BGP neighbor. It's determined now, it's gone to the next domain, and it's got to the end. Right. Now, we talked about something before. We said segment routing can have local control plane, and also it can be external of an entity, and it can compute your traffic and give you the best route. There's a protocol called Computation Engine Protocol. You should connect to this and ask this entity to give me a good route, please. This is an external entity. It can be a server, it can be a router. It works with the PSAP protocol. Suppose you have different IGPs, IGP1, IGP2, two different domains, two different topologies. None of them know about the other because they don't have each other's topology. I told you redistribution doesn't do anything for you because delays, band information, etc. Connections are in topology database, so it's not transferred. I want to have a route consisting of domain 1 and 2. Something that goes from IGP1 and gets to IGP2, but I don't know what their topology is, what is this. This topology. A new add attribute is created in EGP. It's called BGPLS, or link state. BGP links. You tell your IGP to take your topology database information to an external topology. Your topology database, as a BGP update, is sent to an external entity the PSAP exists. So from different domains we collect the topologies. There's someone out there, therefore, who has all the topologies, knows what's happening from 0 to 100. It can carry out path computation, and so I can have routes that I can decide upon locally. I can have routes that PCE controller can compute for me. So through VGPLS, I give it information. Through VGPLS, it collects the topological information about my network. Now, so I have a BGP. Through BGP, my IGP data topology database is given to PCE controller. Now, from PCE, I ask the PCE to give me a good route from node 12 to node 7. What happens? I don't have any routes for it because I haven't done any redistribution. In route at 12, I have no routes, but for 7, so IP road in your on control plane, you don't see anything. You can't get there, but you ask the PCE to give you a route. How does PCE do this? It has it gets all the topology information from PGS. It has all the information through PS3 language. I send a request. Give me a route. It has the routes. It computes the best route. Gives it to me. How? It gives me a segment list. It says, go from this SID to this SID, until you get to the final SID. This SID can have prefix SID, adjacency SID, binding SID, EPE, BGP, prefix SID. It includes all of them. In fact, in route at 12, you get show IP route, but when you ping it, you see. Do you know why you don't have root? Because the PCEA has the root. That is your outside, your external brain, knows everything. You don't need to have it. Says centralized distributed. Centralized distributed is scalable. If everything is centralized, it's not scalable. Everything is local, it cannot be scalable. But it's centralized distributed, it can be scalable at a very large scale, at the national level of the country or a continent. You can do this. Now, so in a general table, segment routing, you can see we compare the old segment routing and modern signal routing. The label in the past was IGP plus LDP. Now it's just IGP. IGP does it for me alone. Fast reroute that MPLS-TE used to do for me is IGP plus RSVPTE. Now IGP does it for me. ECMP understands N to K or N to K, where we had in the past, we don't have this. In the past we had this problem. We don't have it anymore. Now, regarding sRGB, we talked in general about sRGB. I said it's a range through which prefix SID is given. It can BGP or IGP. sRGB, or the range that we want labeling to be allocated to, is manual. It's not dynamic. Yes, you have to give a number from that range. It's manual, but it should be unique. Right. We said sRGB of the routers can be altered by default from 16,000 to 23,999. When you want to do all of them properly because it helps you with the troubleshooting. What does it mean? What I just said, it means I give an index 1 for router 1, index 4 for router 4. This is an index. Index 4 in router 1, it's changed to 16,004 as a prefix SID because it goes from 16,000 to 23,999. Index 4 can become 16,004 in router 2, but in router 3 it becomes 24,004 because the range of your sRGB default has changed. You have changed it. When RCGB of all routers are the same, everywhere you see one index as one number. For troubleshooting, this can help. It can be very easy, but you might want to change it. This is possible. Just a little bit about control plane and data plane.
We have noted that everything is being handled within the IGP. I don't need anything else. How does this actually happen? How is it handled? We have noted that the data plane could be IPv6. At the layer of the service, everything is constant. Whatever you had, you will continue having. If you had MPLS, you had VG plane, or auto conflict, or whatever that you had, it will stay the same. And at the level of the transport level or top level, you use routing, and it's only ISIS system, and you don't need anything else. Now, as you fully well know, ISIS is actually existence of certain TLVIs. What is TLV, ISIS, TLV? Any extra data that you want to transport, you could do that. For example, you don't have authentication, you use this. That is to say that when you're actually activating this feature, you have a TLV with a special system, and it actually transfers the data within. For any extra data, you have a TLV. Now, there is something called sub-TLV. It is when you want to provide more information about TLV. And by default, TLV is the kind of data which is not sent, but sub-TLV is actually related to the TLV itself. I talked about prefixing. I have a router, and I'm actually working with an administrator, and there is a special procedure, and how can I actually provide the time? Through IGP or OSPF. My prefix could be changed within different levels, all the different numbers that we have. My adjacency seed could be changed within 22. So if I wish to teach my adjacency to someone, I use this procedure, and I would use the TLV numbers that I already told. I may be a router, ISIS. I'm using an old ISIS, and I don't understand segment routing, so I come and speak to you. who are experts in the field. So how do I know that you understand segment routing? One ISIS router with the number of 242 through this TLV, it tells me whether it is capable or not. The OSPF is actually within the OPAC procedure. This is the TLV number, and we also have a packet in the wire shot, and we can see this. This data is for ISIS, and we are using this TLV. If you look at this, our TE equals 22. Now we would say that what is it actually changing and transferring? It's 165, 242. So we open the packet, and I don't know if you know this above or not. Can you see my mouse? And you have to understand how it works. The adjacency seed. In 135, I will send you the prefix seed. I have opened it here. 135. We go to sub TLV, and there is a sub TLV which is actually working on the TLV, and the figure is very fixed and clear. In the TLV of 22 is the adjacency seed. So where was the sub TLV? Over here, you see that the gray and you see the blue, and that it's TLV, and the other ones are the sub TLV. For 22, it's actually the sub TLV. For 135, it's the sub TLV of 3. The sub TLV 3 and TLV 135. And it goes actually into sRGB. We understand something about the generality and go through the different C types. We talked about previous technologies, and we talked about these issues. In the service provider, you might actually think about this. It's actually a very good solution, which is still being used in different operators, is unified SIM PLS. You have different domains. You would use IGP and LDP and RSVPT because there are different ASs, and you would be able to use different modalities. You have A, B, C. So this is BGPLU or label unicast. Ultimately, you go to your service layer, and you are using different protocols. You go one step ahead. You can actually summarize the first 3 in IGP, so I don't need anything else in this regard. I use BLGP, and this is again the connector between the different factors. This is for me to understand this procedure with the next one. In the next step, I could actually remove and exclude this because the one who would join us together is PSEP. If you remember, in the previous slide, we have the different topology, and we would use the PSEP protocol, and you would choose the best method. You could actually remove this and go through the next stage with fewer protocols and with a higher efficiency. There is also another application. Suppose that you have one VPN service transport. What happens is that your service label is constant and it changes into IGP. And you can use ECMP because it exists in the segment routing. And of course, you have the process undertaken. Now the question, some part of my network is LDP and the other one is segment routing. So I should be disconnected with the previous procedure. I can't go from zero again and, on one day turn it into routing. I need to do this step by step. Some part of it is segment routing and the other one is LTP. Is there any internet working between the two? Yes, there is. If we want to go from LDP to segment routing, it could happen with no conflicts because it actually gets to the border router, which exists right there, and automatically it goes through the prefixing. But before I continue, let me just add this point. Suppose that all your routers are LDP and you want to migrate completely up to segment routing, and they have LDP, and you have the SR, and you're activating this. You have LDP, and what it's actually doing right now, it's using LDP or using segment routing. It is actually using this procedure. Unless you have this router which goes on, and with the command that you are supporting, you are using your own data command. Now, what is your traffic? You will see the blue part, and the green part is to do with the segment routing. You can go from router 1 to router 5. They think in different ways. They're all using IGPs, and they're making their choices. The data plane, your data plane, is going to your LFIB or level information base, and it actually puts the information there. I'm actually in the table right now, and I put two series of different information in my table. We have the inbound and the outbound for segment routing. This is actually formulated for segment routing, and the procedure would become clarified. And this also happens for LPD. But by default, I'm using LPD unless I wish to see what the command routing would be. When I say this, that the traffic would be taken away and it would be moved from this station. In the previous example, the entire procedure has been put there. But in the previous example, I would use different segments and routing. And then I could go on to the segment routing. You have a procedure right there at the beginning, and the LDP is formed. Now you need to have some information at the border, and without any distortion, you would be needing to use the data. And of course, it will be automatically copied to the other side, and your LSE is completed. But when you want to go from SR to LPD, the entire procedure would change. And so from the viewpoint of SR, you do not have any seats. Therefore, you could actually understand how the procedure is in a virtual world. This is done by mapping survey, and I understand that the different seeds and the different definitions, and I would be able to continue my packet automatically. The green is SR, the blue is LPD, and the LSP is actually formed. The mapping server injects the data. The LSP of the green part is actually formed, but it hasn't reached the end yet. It's not available. The information for my LPD is copied, and it is actually the SR which goes to the end of the pack. This is highly important. Look at the final flash. It's blue, and this is how we understand it. The final flash is doing segment routing, and this is an LPD. That is to say that we are talking about the certain aspects of a segment routing. They have both data planes, and in its final decision making, it should actually make the decision of where to go, and it should actually use the final SR. Traffic protection is another concept.
Yep, there's a protocol, or rather, there's a mechanism called loop-free alternate. If I may add a point to old MPS traffic engineering that used IMPs, it was everyone liked it because it was fast rerouting, but there were problems because didn't work. This fast rerouting wasn't that optimized. The client says there was a project. We had a project. The convergence time IGP was going to go from 9.5 seconds to 200 milliseconds. We did this in 6 years. Whatever optimization that we needed, we put in within our IGP. We got to 200 milliseconds. We couldn't go further. And then we had a new mission. Go from 200 milliseconds under 50 milliseconds. We couldn't use IGP optimization. We decided that we need a pre-computed path. Now, what does it mean? That means I'm going on a path, a pre-assumed backup plane should be put in my data plan. As long as it's down, we should use that. So LFA, or loop-free alternate, was added. Old LFA has some problems. It's not 100% coverage, and doesn't choose the most optimized route always. 75% to 90%. To increase that 90% in the project that they had, to go from 95 to 99%, they used a mechanism, remote LFA, using LDP protocol. But again, they didn't have 100% coverage. That is, topology could have conditions where you would not be able to choose a pre-computed path, for example. First of all, for you to choose a path as your backup path, you have some conditions. They are here. The first condition is, suppose S wants to get to D. S wants to go to D. The primary route is from up there. Backup route is from down there. So if the upper link is cut off, the end node N should be used. N can be LFA node, and if its route to D is shorter than N plus S. That's shorter than going and coming back. That's the first condition. Path is loop-free because IGP says you should go through this route. Between 2 and 3, there must be a cutoff. So I want to choose a backup path, backup route. If the connection between 2 and 3 is disconnected, do has to go through router 6. There's no other route apart from 6, router 6. But LFA doesn't choose this because route 6 to 5 is longer than 6 to 5 through 2. That is, 6 now has two parts, two routes, one going from down there to 5, the one in the upper from up there. From 2. It is choosing that route, so it will never choose this route. 6 itself is choosing that route, so it can't satisfy the first condition. So LFA in this condition doesn't give you any backup routes, so the coverage of LFA is never 100%. We want to optimize it. What should we do? A new concept in segment routing called TIFLA, topology independent FLA, is introduced. It's not important to me how much it costs. I'll choose a backup route for you. How does it do this? We assumes that the link is cut off as post-convergence. LFA always calculates pre-conditions, but TLV says assume it's cut off. It prunes the OSPF or ISIF tree is formed again. That link doesn't exist, so the existing link is through 6. So it uses, look at these vectors, initial classical LFA. LFA is blue. The orange one is post-convergence. The green one is TILFA. Here you can see there is no blue route, and LFA can't choose anyone. So either there's no coverage, or it's not optimized. The top one is 100. Cost is terrible. Your traffic shouldn't go from PP to PE and return. But the old LFA did that for you. It would send your traffic from up there. But TILFA chooses an optimized route. It goes from down there because it prunes the middle link in its head, if you like, and then chooses the new route. Now, in TILFA, we want to get our packet to the destination. For this, we have to choose a router that would not have a micro route returning. So if you send your package from 1 to 5, PAN shouldn't return it up. It should continue forward. For this reason, you should choose a Q space and a P space. Q space are routers that give the best route to router 1. It's not through the middle link. It's not through the red link. Q space includes routers. In order to get to router 2, don't use router 1. But these two together is a space where there's no micro loop. It doesn't return. It continues. With the labeling that is given, the traffic is transferred. Now, we can have different conditions where this double tagging can occur, or one tag is given. On the previous slide, you didn't need any extra tags. A, it says I want to go to 1. It looks at post-convergences. There's no other routes with the original label. It sends it forward. But there are conditions where we have single label. All right, so that is a PQ router. So it's several hops further down. Now you have to get to that first hop. So you have to get to the first point first. In order to get there, you have to inject the label. This injection happens in router 1. We get to number 5. 5 takes it to 4, and from 4 onwards, there's no micro loop. The traffic doesn't return; it continues. Now, sometimes the P space and your Q space don't match, don't overlap. Rather, they don't overlap. You don't. So you should use an extra label stack. You should get the last router of your PSP, and then with an adjacent thing, you should send it to the adjacent router, and then you get to the adjacency SID is in blue. In router 4, with adjacency C, you go to Q space and from there you move on. So P space to Q space. Now, the same thing can happen jointly for LDP traffic. Now, we talked a lot about RSVP TE. It's a bit repetitious if I want to talk about it, so I'll move on. Traffic engineering in segment routing becomes SRTE, segment routing traffic engineering, SRT. In older SM methods, you had to have a tunnel and configure it, but in SRTE, you can move forward according to the policy, give a policy. I want some such trace, I want my bandwidth to be such and such. We'll go through these routes, through these nodes, through this route, and it does it. Right. You have such a topology with different domains, each having its own prefix SID. Router 10 as PCE, 11 is BGP route reflector, big pardon. You go through BGPLS, you get the topological information is given to PCE. Now, my PCE has the topology of both domains. All the routers should be connected to PCE through the PZ protocol. In order to transfer the BGP protocol, you get connected to the BGP reflector, so the problem with the IGP will be resolved. Now, through route reflector, I have all the BGP routes, and through PC, I have the whole topology. Now, suppose router 1, where there's a network, between 22 and 21, there is a link, probably. Maybe it's been deleted by mistake on this slide. Between 22 and 21, there is a link between the two routers. A prefix is being advertised. It's given to 22. It sends it through a community. You can choose have a route according to SRTE, according to BGP, Community Manix Hub of BGP. And in the first router, you can say, if I get this community, I want to go this way. Or if this community, I get this community, I want to go through a a route that has more bandwidth or less delay or whatever. So I teach this route to 22, teaches it to route reflector, teaches it to router 3. Router 3 talks to PCE, gets the best route, gives it the binding SID. In the binding SID is determined which route should be gone through to the final route. My colleague Mr. Tawajjo, is going to continue with SRv6. Good afternoon. My name is Tawajjo. This is the end, towards the end. Maybe you're too impatient. I'll try to move fast. SRv6. Rasul mentioned we have two data planes. We can have two data planes for segment routing. One is MPLS, the other one IPv6. What's implemented at the moment in the networks, or being implemented, is now according to MPLS, on the basis of MPLS. But in the future, MPLS data plane would be replaced by SRv6. Certainly, we know now that IPv6 as a is used as a reachability protocol, to be set on two devices, for two devices to be able to see each other and to be connected together. But with the problems that Rasul mentioned, for example, RSVP, what are you going to do with RSVP? Well, we talked about this. We found we have something called TE, SRTE, etc. And we don't need LVP and MPLS protocols that are extra. We use IPv6 instead. This had to do with underlays. What about overlays? you have something called UDP and VSTAN. We know VExtend and UDP, VExtLAN and UDP are to expand the tenant IDs. When, for example, we want to extend the VXLAN to another data center, we need to use extra protocols. What segment routing gives us is that we can be replacement for these overlay protocols. Instead of increasing the headers, delete them and use segment routing as an overlay protocol. The next point is the existence of service chaining, or NHS, that we have in our existing networks, or NFVs. NFVs is quite hot and being used a lot. But segment routing says it can replace these NSHs, that is in the header of IPv6. We can determine which of our devices can be on the way of the packages. The important and basic point that we have is that today's topic in traffic engineering is implemented on devices, but when we talk about today's applications, it is the application that wants to determine which route I want that would have the least delay. That is, it is the application that wants to tell the network which route is for me, or created a route for me so that I would have the least delay, etc., whatever bandwidth. So we should allow the application make decisions for our network. This permission is given through segment routing. We can do this. And label stack that Rasul talked about, instead of being carried out by devices, is done by the applications and the servers. So in order to do this, all the servers and applications should we support MPLS at the moment to be able to give it labels or write a TE, but using segment routing, because the header becomes IPv6 in general, application doesn't need to have terrible or strange hardware to support IPv6, because our OSs, our applications are working with IPv6.
I'm sorry, I'm not feeling very well. I apologize for my voice. IPv6 has a very specific header, and of course a source address, a destination address, and it also has a next header, and it becomes very clear in the header what actually comes about and where we get there. For instance, if in the next header, if there is a number of 41, that means IPv6. That means IPv6, and then we'll have another approach. And if it's 4, it means that we will have IPv6 again after it. There is 43, the next header, which is the routing extension. This routing extension is actually involved in the router files, and we see that we have them in different years as being added. And if 43 is actually set, we have 4 different fields as the next header, and header, extension link, and also segmentation left. The next header is very clear. It could be another IP, it could be UDP, or it could be anything else. Header extend link could be actually conducted, and it is not very, we don't need to process this procedure. The routing type is what we can actually include, and to see whether it is active or not. If the amount of 4 would be put there, it means that, and of course towards the end you have the segment left, and of course we will talk about it. If you have 43 and 4, you understand that SRv6 is actually the procedure of this package. This is a packet which is being captured, and you see the routing extension and the routing which is good enough here. And this is something that Rasul has already talked about. Right now you have router ID, and actually it looks like this very much, and it's very much like IPv6, but of course it could be the equivalent of IP6. Let's talk about one example over here to see how SRv6 actually operates. For instance, imagine that one package wants to go from 1 to 4, and there is something which is not being supported, and A1 is actually the packet, and it's actually a segment routing header, and there are specific numbers there. The source address is A1 if you see it, and the destination address is A2. If we scroll down a little, on it's actually the last it's the last segment list of my ID. Therefore, segment list is in the order of the hop, and it's actually the last hop on the procedure, which the segment list of 0. And at the right hand side, the SL equals 2, and that is the number of the nodes minus 1. In other words, n minus 1. Therefore, this header, we actually insert it, and it's called SRH. The destination address should be changed because it's actually taken away from the segment list, but the source address remains the same. And now we're talking about the next hops. It's not supporting SR6 because it is actually an SR6. We can see the next destination address, and we will find it, and we forward it to the next stage. Therefore, it is not necessary for all. It's not necessary to support all these procedures. In the second node, SL is actually number 1, and the destination address is actually the one in the middle. And it will remain in our segment list, and the previous hubs is still observable. And ultimately, A3 will act in this way until we reach the segment list of 0. When we get to this, there is nothing processed, and the package is actually taken away, and it reaches the destination. Up to now, Rasul was talking about it and explained, and I just gave you SRv6. I didn't want to go inside the details. There are different companies in the world which have been able to operationalize segment routing. You see a list over here. They've either started or they are in the process of starting. The future of networking is segment routing. Now, when we have SRv6, definitely it will be much stronger. Right now, Linux and it's supporting SRv6. Cisco saying that I'm deploying it on other devices, and it has done it on the NCSS and the other brands as well. Now, if we want to work with SRv6, we need to work with them and use them alongside these large companies that you see. In Iran, for the first time, we are doing segment routing in the infrastructure telecommunication company, and of course it will be discussed very soon. Thank you very much. A very quick question. You say that you're doing it right now in the telecommunication infrastructure company. This is going to be a very long project, or that we might see it in just 6 months, in the next 6 months, or about a year. Generally speaking, it's a near future. It's actually within this calendar year that we would be able to operationalize it in Iran. What about SRv6? As I noted, SRv6, because the platforms don't support all of them, For instance, it's commuting segment dash routing dash net. And you can actually go there and see what developments are happening over there and how SR6 is being implemented. But as I noted, the other projects are being worked upon, and probably in the next year it will happen. Now, my last question is about private companies. Do you know that the private companies are service providers and whether they're working on their segment routing? And I'm not very sure about each and every single one of them. Thank you very much. Just one point. Uh, Actually, in the Middle East, nobody has used them, but probably it's actually the first time that in Iran it's happening, and it uh, might happen. Thank you very much. If you have any other questions, yes, please. One question regarding TE about segment routing, and do you actually support the transport? Yes. They're all targeted LDP. They're double tagging. It could be segment routing. It's not really so different. It goes within the service layer, whether it's ATOM or whatever it is. They become layers of service. Your top layer could be segment routing or LTP. There is no difference in the segment in the services layers. One problem that we had, and then we had to use a TE when the traffic is pure MPLS. Right from the very beginning, you have this issue. Some devices are not being supported to be balanced. So we had to use, what we did was on two TEs, which are the same in terms of cost, to have the links and to operationalize them. In segment routing, we should work on adjacency CETA and to do it on the equal balance. No, not at all. Your point should be clear, and automatically it should be clear where you could have the different procedures. And of course, the new capability in the next versions is actually UCMP, unequal cost load sharing, and it's within the OSPF. So the concept of weight that you had, and you could do unequal load sharing. You could do it in ISIS, and you could actually add the concept of delay to this segment routing as well. In other words, the you could actually think about the difference between the films, and I don't exactly know the formula, the mathematical formula, but you would be able to see the delay. If within the OTN, if one of your lambdas is actually changed and the procedure would be changed, the delay will of course be more, and the delay could be calculated, and the routers next to it will learn and see how it operates, and it could be reconverged. The issue was that in IGP, it could not be put. Of course, it cannot be implemented completely and fully, but in the Cisco lives that you see, and also the seminars that you see, such as Nokia, they're all being added. The next technology supports UCME and OSPF, and also delay, and also bandwidth. Thank you very much. My name is Parsa Yousefi from .co Bandar Abbas company, and I'm just one question about the presentation. Maybe there are places that the cost could be the same. Could we also have MTU, and for example, could we make those changes as well? MTU has not been added in its metrical, but can you give an example where the MTU is? No, I don't have any specific example. And with the jumbo frames, where could what we have seen so far is delay and bandwidth, and also unequal load sharing. But have not seen anything in the form of metric MTU. I don't have anything in my mind. Thank you. If there are no other questions, well, no other questions. Thank you very much. Thank you. Now, this was the tutoring at the end of MENOG. Have a very good day. If you have any other questions, points, we're here at your disposal. We can continue talking. Thank you very much.
نه بهش گفتم اتفاقا بهش گفتم مطمئن همین یه دونه یا مشتاق بگی مدیر اون شد بیا همین